Bernoullis equation has got a lot of applications. One application is lift of aeroplane, right? How does an aeroplane go up? The wings are designed such that the speed of air is more on the upper side of the plane and speed is less. So here, because travel a larger distance, V is more. Air has to travel a larger distance on the top side. So V is more. Here V is less. Wherever velocity is more, pressure is less. So here pressure is less. Here pressure is more. And this difference in pressure causes the plane to lift up. So lifting of an airplane is also an application of Bernoullis equation, conservation of energy. Where velocity is more, pressure is less. In this lesson, we are learning an important application of Bernoullis equation, that is speed of efflux. This is a tank. This tank is filled with some liquid. So some liquid is there in this tank. And we make a hole in this tank. So we make a hole here. And through this, liquid will come out with some velocity v. That v is called speed of efflux. Suppose the height of the tank is capital H and say the height of this hole is small h, or we can say this as h. Let us call this as h. The difference in height of the top level and the orifice, this is orifice. Orifice is the hole through which liquid is coming out. So h is the height of that, h is the depth of that orifice from the top of the tank, from the top level. So now we want to apply Bernoullis theorem and find out this speed of efflux. Here this is open to atmosphere, so pressure is P0. Here this is also open to atmosphere, so pressure is P0. So there is no change in pressure. Pressure here is same as pressure here. This is a big tank, so the level is coming down very slowly. So the velocity here, you can approximately take it to be 0 because it is coming down very slowly. Compared to this is nothing. So velocity is 0 there. And the height difference is h. So if I apply Bernoullis equation, pressure P0 is the pressure there, plus height we measure from here because that height difference is important. So pressure plus rho gh plus half rho. Velocity here is 0 almost, so 0 squared equal to P0 is the pressure there. Height is 0, rho g, height is 0. This we are calling as, this is our reference frame where we say height equal to 0 because the height difference is important, the actual height is not important. So rho gh plus half rho v square is the speed of efflux, that is the velocity here. So now P0 cancels, so P0 cancels. This is nothing but 0 because you are multiplying with 0 square. And this is nothing because again you are multiplying with 0. And rho cancels now from both sides. So V becomes root 2 gh. This is the speed of efflux. V equal to root 2 gh. So understand this. There is a big tank and we are making a hole in that tank. So that liquid is coming out. The difference, height difference between the top of the tank, the top level of the liquid in the tank, and the orifice, that height difference is h. Both are open to atmosphere, so pressure is P0. Velocity here is almost equal to 0. Height here we are taking it as 0, so difference in height is h. So P0 plus rho gh, the gravitational head, plus half rho velocity is almost 0, that is 0 square, equal to P naught plus rho g, this height we are calling it 0, plus half rho v square. We get v equal to root 2gh. So this is very important. This comes from Bernoullis equation, and from here we get Torricelli's theorem. Torricelli's theorem. This Torricelli's theorem tells us that the speed of efflux is same as the speed that the liquid would have attained if it was falling from the same height. We know free fall. Suppose something is falling from this height, right? What is the speed it picks up? The speed it picks up is given by v square minus u square equal to 2as, right? This equation we know. Here the initial velocity is 0, so this becomes 0. This is acceleration due to gravity g, downward we are taking as plus, so this is h, so v becomes root 2gh. So this liquid, if it is allowed to fall freely from here, this same height, it would have picked a speed equal to root 2gh. Now the speed of efflux also comes out to be root 2gh. So that is what is Torricelli's theorem. Torricelli's theorem tells us the speed of efflux is equal to the speed that the liquid would have picked up if it was allowed to fall freely from the same height. That we call it Torricelli's theorem. This was given by Evangelista Torricelli. Now we want to find the range. How to find the range of this? This liquid will come from here and fall to the ground somewhere. We want to find range. So we need the time of fall. Once we have the time of fall, then v into t will give us the range, because the horizontal velocity is not going to change, right? That is projectile motion concept. It's coming out speed v, so distance traveled will be vt in the horizontal direction. So v into t will give us the range, right? Because horizontal velocity is not changing, there is no force acting in horizontal direction. Now to find the time of fall from here to here, study vertical motion. This is like free fall, and time will be given by root over 2 into this height into g, right? Root over 2h by g. So root over 2h by g, that height is nothing but h minus h. So therefore, the time of fall will be root over 2h minus h by g. This is the time of fall, right? Time to fall from here to here. And this, if you multiply with v, we will get the range. So range will be equal to v into this time, t. v is root 2gh, and time of fall is root over 2h minus h by g. This g cancels out, right? So we get the range as 2 root over h into h minus h. This is the range. 2 comes out because of this root 2 into root 2 multiplied by h into h minus h. This gives us the range, right? This is the range up to which the water will fall. Now suppose you want to maximize this range. How will you maximize the range? So R is 2 root over h, h minus h, square both sides. So R square equal to 4h, 4 is a constant, we can leave it outside, into h, h minus h, that is equal to 4 h minus h square. Now range will be maximum, this is maximum, right? So we can say range will be maximum when y equal to h minus h square is maximum. To find maximum, we differentiate this with respect to small h. Capital H is a constant, you will get h minus 2h equal to 0. So from here, we get h equal to h by 2. Therefore, for maximum range, we must make a hole in the center of the tank. Then the range will be maximum. So range is maximum when h equal to h by 2. This you can check by taking second derivative as maxima or minima. So d2y dh square, if you differentiate again, this will give you 0, this will give you minus 2, that is negative, therefore it is maximum. Therefore range is maximum when the hole is at the center of the tank. Range is maximum when the hole is at the center of the tank. Another important thing you see, this is very symmetric in H and H minus H. So if a tank is there and we make a hole, this is full of liquid say, and we make a hole at a depth H from the top or at a height H from the bottom, in both the cases the range will be same. RH is equal to RH minus H. This is very important. Range is same whether you make a hole H below or H up from here. RH equal to RH minus H. Very important, right? RH, very interesting also. You can try this experiment. Take a bucket full of water or take a water bottle, make a hole H below the top, H above the top. Okay, here the speed will be more, so it will fall here. Here the speed is less, but the range will be same. R will be same. Right. Now, suppose you want to find the time taken to empty a tank. Suppose a tank is there, whose cross-sectional area is A, and here you make a hole at the bottom of cross-sectional area small a, right? And the height of the tank is H. To find the time taken to empty the tank, we will do integration, right? Because the height will keep on changing, so speed of efflux will keep on changing, flow rate will keep on changing. If you do that, then we find the time taken to empty the tank is given by E by A, because if this A is more, it will take more time to empty. If this area is bigger, this whole orifice, it will take less time. So we get A by A root over 2H by G. This formula you can just remember, this gives us the speed of efflux. No, this gives us the time taken to empty the tank. Now we have seen that the range is maximum, R is maximum when H equal to H by 2. That means if you make the hole at the center of the liquid level, right? Liquid is say up to here and you're making a hole here, we get R as maximum. Range is maximum. That range formula is given by 2 root over small h into h minus h. Suppose we put h by 2 in this equation. So what do we get? H by 2, h minus h by 2. That is also h by 2. So maximum range is equal to h. So range is maximum when you make the hole at the midpoint, and that maximum range is equal to capital H. Right, remember that. Now, if a cylindrical pipe is there, flow of liquid through a cylindrical pipe, and you want to find the velocity at some point, right? This liquid is flowing, so the velocity will be like this. At the midpoint, the velocity is maximum, and here the velocity will become less, and here the velocity is 0. So you want to write the equation for that velocity. So that velocity is given by the pressure difference P1 minus P2 by 4 eta L, the length we are considering, multiplied by the R, this radius R square, minus this wherever we are trying to find the speed, so that is small r. So R square minus R square. This gives us the velocity at any point in a cylindrical pipe, P1 minus P2 by 4 eta L, R square minus R square. Eta is the coefficient of viscosity, right? So this gives us the flow speed at different places, different points on a cylindrical, in a cylindrical pipe.